Hello and welcome to our first exam. It's very exciting, I know. We're like halfway through our course now, which means that we're going to be taking half of all of this content that, we're going to learn through this course and test you on it. So our class has two exams, one here at the halfway point and then one at the end. So kind of like a midterm, I guess you would say. And the purpose of this video is really just to help you understand what kind of topics are going to be appearing on the exam and how to best prepare for that. So this is kind of an optional video, just something if you're wanting a little bit more guidance on what you can expect in this exam. But I will say the, too long didn't read version, if you want the shortcut version, would just be take the practice exam. Right? There's a practice exam available for you through our homework website, the Pearson, used to be called Mastering Engineering, Pearson Mastering Engineering. That website has a practice exam for you. It's not very long. It's much longer than the actual exam, but it's going to prepare you really, really well for the kinds of questions that you might see on the exam. So they're going to look very similar to those questions, maybe a little bit shortened, but it covers all of the topics that we've gone through so far. So anything that you see in that practice exam could pop up in your regular exam. So if you feel pretty confident and pretty comfortable with everything going on in that practice exam, then you're probably going to do well on the actual exam. They're meant to be pretty similar, give you an idea of what's on it. The major difference is that practice exam is really long, it's not timed, it has way more questions, whereas your exam is only going to be 4 questions long and you'll have 2 hours to complete it. So you can use that practice exam and time yourself for 4 questions and see if you're, doing well on the pacing, on the timing of everything. But again, some things may be shortened for the exam and a little bit simpler. The goal isn't to trip you up with like hard, tricky math. The goal is to see that you're understanding the concepts that we're working on and can have the critical thinking and the thought process to work through those problems, work through logically, step by step, how to approach problems like this. Because that's really what we're doing in statics. We're kind of building your logic and critical thinking here before you get into the higher level engineering classes, even if you don't necessarily use statics in your higher level engineering classes. So with that, we're going to kind of talk about the topics that you're going to see and some things that I kind of, expect you to know or expect you to have memorized. You do get to have a formula sheet. The formula sheet is on our D2L website, so you can see it there. That is given to you, and that's the only form of assistance that you have outside of your own brain, right? Closed internet, closed notes, closed books, closed homework, closed everything except for your exam and that formula sheet. So anything that's not on the formula sheet, you'll need to know. You'll need to have memorized or know how to manipulate if it's not given to you directly in the problem. So some things I'll say right off the top here, some things you might want to know that won't appear on the formula sheet or things that would just pop up that I would expect you to know. So for example, like sine, cosine, tangent. Knowing how each of these trigonometric functions work, SOHCAHTOA, how the angles go with each other, maybe special triangles, understanding, how to use the ratios in a 3, 4, 5 triangle. Those kinds of things I would expect you to know how to do, know how to manipulate for your problems. Another one I might expect you to know, I would expect you to know the quadratic formula. So like a squared plus b squared equals c squared. Not given to you, but it's something that you've probably used enough times now. You know this equation well and have it memorized. Another big one I would say is F equals ma, right? And this is an important one because sometimes you're given the mass of objects, but we're often working with forces in statics. So sometimes you'll want to use, force is mass times gravity. and knowing that gravity is 9.81 meters per second squared, or in US units, 32.2 feet per second squared. Those would be really good things to have memorized, to know, and know how to use them, know when to use them. Some other things would be like Cartesian form of vectors, understanding the I hat, the J hat, and the K hat, and which components each of those go with, right? So this would be like your X component of your force, your Y component, and your Z component is K. And then some like basics of vectors, so like how to add and subtract vectors, in addition to all of the other stuff that we do with vectors, the very, very basics of vectors, addition and subtraction, finding the magnitude of a vector, which again goes back to our quadratic formula. Square root of the X component squared plus the Y component squared plus the Z component squared would give you the magnitude of the resultant force. So these are the types of things that I would expect you to know, kind of basic things that we are not really learning in this class, we're just kind of using in this class, that you should know how to work with. Otherwise, everything else should be either stepwise in the process or on your formula sheet. So let's go ahead and take a look at some of the topics that you're going to be seeing. Right? For this exam, we're going to be covering everything that we've done so far in this class. So that's our first 4 weeks of class. It does not include this week, this 5th week. This week is trusses. There are no trusses on the exam. It's only weeks 1 through 4, which I believe is chapters 1 through 5 in the textbook if you're following along in the Hibbler text. So for us, what that's going to be is essentially vectors, resultant forces, and then the 2 big buckets of equilibrium problems that we've done. So equilibrium of a particle and equilibrium of a rigid body. Let's kind of go through, what we've done in order so far. We've done lots of things with resultant forces. This is really kind of where we started the class, was in vectors and resultant forces. So knowing how to find a resultant force. Right, so you could be given, this could be in 2D or in 3D. Maybe you're looking at a post and there's a bunch of forces acting on that post. Can you find what the resultant force is? And that could be in Cartesian form, or it could be asked in just like for the force and the angle that's acting on it. Or in 3D, you might be given, the force and the alpha, beta, gamma angles. Pretend that's a gamma. Gamma, that looks better. And that would be your IJK, Cartesian coordinates. So it could be either. Could be in 2D, could be in 3D, could be any different type of notation. Whether you're given those or whether you're finding a resultant force or finding a missing force, like given the resultant, find the missing force, that kind of thing. Converting vectors into Cartesian form is also another topic that may come up. Finding a force in Cartesian form. Again, that's your IJK form. And then another big one that we did with just the vectors here, we worked a lot with dot product, but specifically with dot product, it was finding the angle between 2 vectors. So there may be some kind of dot product problem that we need to find the angle between 2 vectors. Could be in 2D or 3D, probably in 3D since we're using dot product here. Finding the angles between 2 vectors. And that was really our big vector portion, right? We did 2D and 3D, trying to find resultant forces or learning about Cartesian form, finding angles between two vectors. Then we moved on to really our heart and soul of statics, and that was equilibrium problems, starting with equilibrium of a particle. Right, so this is when we were just looking at certain points, right? We would look at, maybe you have, everybody likes the traffic light problem, right? We had traffic lights. And so here, we weren't looking at this whole string as a bunch of, as like one big body. Instead, we were looking at these individual points, right? Taking a free body diagram at these individual points to solve for the different forces. So your equilibrium of a particle, right? Just looking at specific points. What is the equilibrium of this particle? And we primarily did this in 2D. We did a lot of these in 2D, where it was maybe find the missing force, or, given this amount of sag, what is the weight of the flower pot, for example? Those kinds of questions. Springs and pulleys we also saw come up. Maximum weight, those kinds of things. It's very unlikely that I would give you a 3D version of one of these equilibrium problems. It's most likely going to be a 2D problem, right? Because 3D problems, they're a little bit harder to, honestly, they're a little bit harder to make a fair question out of because they can be really hard to read the diagrams. So it's more than likely going to be a 2D equilibrium of a particle problem. And if it is something in 3D, it'll be something a little bit simpler. The 2D problems will be a little bit more complex. But again, finding your equilibrium, so just doing your summation of your x forces and setting that equal to 0, and summation of your y forces and setting those equal to 0, and then solving for whatever item of interest you need. So that's our really big one, right? And this is really the heart and soul of statics. These equilibrium equations come up again and again and again, and it's really kind of the basis of our whole class. So if you're really struggling with this concept of equilibrium, this is probably going to hurt you the most for the rest of the class, because it's this concept that carries us through all of statics, that we're taking all of the forces acting on something and setting them equal to 0, right? It's not moving, or at the very least it's not accelerating. So it's just stationary, or it is in static equilibrium, right? All of the forces cancel each other out, essentially. Heart and soul of this class, the most important thing that I hope you walk away with is just understanding how we apply and why we apply these equilibrium equations. So after we did the equilibrium of a particle, we then moved on to learning about this new concept called moments. And there's a very good chance these moments are going to appear on this exam for you. We did a lot of different things with moments. For example, we first learned about moments. We learned we can find them in a scalar form, which is just force times distance. We can find them in a vector form, which is going to be our cross product, of R cross F, right? A position vector crossed with a force vector gives us a moment vector. We learned how to do moments about a specified axis. So doing the unit vector of our axis of interest dotted with that R cross F vector. So that's about a particular axis. We learned about couple moments and how we can take two moments that are equal and opposite, separated by a distance d. right? And different ways that we can manipulate those. So those are essentially our big concepts with moments. But more than likely, it'll be applications of these concepts. Instead of just asking you to find a moment, it could be, you know, finding an equivalent force. We did a lot of things with equivalent forces. So these are moments. We also did a lot of things with equivalent forces and finding the locations of those. Which we used a moment to find those locations. So maybe we had a bar and we had some forces acting on this bar and we found the equivalent force. Say it was there. And then to find this distance, we would have to take a moment, right? Get F times D gives us our moment. So summing up those moments, again, using summation of fx, summation of fy. So those are our big things with moments. So we may be asked to calculate a moment or to use a moment to calculate something else, but moments are going to appear on your exam, especially because they appear in our second big equilibrium topic, which is equilibrium of a rigid body. So our other big equilibrium thing that we talked about, equilibrium of a rigid body. Our rigid bodies, that was really anything that we couldn't reduce down to a single point. So one we like to use a lot is beams, right, where we have multiple forces acting down on these beams, and then you know, say solving for maybe the reactions at the end, something like that. Solving for those reactions, or you know, sometimes there are applied moments on these beams. Again, moments may come back. They're just the ability to solve for a full body here, equilibrium of rigid body, with our summation of x forces is 0, y forces is 0, and the major difference is now we also have summation of moments is 0. The moments are the big thing we add, the big difference in the math between our equilibrium of a particle at a single point and the equilibrium of a rigid body. So it's also going to be really, really important that you're able to determine which kind of equilibrium you're looking at. Are you looking at a single point, or are you looking at an overall body? And knowing how to distinguish between those things is going to be really, really important in making sure you're using all of the right equations for your equilibrium problem. So these were our 2D equations. We can also see equilibrium of a rigid body in 3D, where now not only do we have summations for all of the forces in the x, y, and z directions, but also moments about the x, y, and z axes. All of those equal 0 as well. Right, so this can get a little bit complicated because now we have 6 equations. We can have up to 6 unknowns. These would be, you know, a lot longer of a problem, but it's very possible that I may give you some kind of 3D problem that you'll have to work for equilibrium of a rigid body. So here it's really, really important that you know how to set these up and know the steps to solve. Because again, I do give a lot of partial credit, you know, especially if you just make a simple math error. I'm very generous with partial credit, but you really have to know your steps. Write out everything that you can. Write out all of the steps that you're doing as you're working through these to get as many points as you can. I think that's mostly it. Let's see. With this equilibrium of a rigid body, when we're working with beams, it's also really important to know whether you're working with a pin, they often look like a little triangle, or a roller, often looks like a circle, a fixed end, where it's just attached to the wall, or if you're in 3D, some of the other, what a 3D pin looks like, so it might look like that, maybe with a bar through it. A roller might also look like a rocker, a ball and socket joint, those kinds of things, what those joints look like, and what all of the forces are on those joints. So like a roller, for example, only has a force in the y direction, only has a force normal to the surface that it's on. But a pinned connection has two directions of forces. FY. Right, so knowing what all of those reaction forces can be for the different, what do you call them? I guess fasteners. The fasteners, whether it's fixed to a wall, where fixed has a moment reaction, for example. So understanding what kind of reactions occur at each of these different kinds of joints, each of these different kinds of end points, contact points, whatever you want to call it. And then the last big thing I think I have on here is distributed loading. Right, so this kind of goes with everything in finding equivalent forces, and especially in finding your equilibrium, is those uniformly distributed loads. So it could be, you have a beam, maybe you have a distributed load that's rectangular, maybe you have one that's triangular, maybe you have one that's really weird. Right, so understanding how to solve for an equivalent force for each of these different distributed load regions. Right, so for your rectangular one, you can just find the area of that rectangle, and we know that that the equivalent force happens halfway, right, to the center of that rectangle. And being able to find the centroids of where this equivalent force for the distributed load occurs. So I'd say distributed loads are a big one. And I think that's about it, which is still a lot. It's a huge amount of content that we've covered so far, and it can be really overwhelming. But just know that you've put a lot of work in so far, right? If you've been working the homework problems consistently, there's a very good chance that you're going to be well prepared for this exam. The homeworks are going to look like the practice exam, and the practice exam is going to look like your regular exam. So if you've been putting in the work and you understand these concepts, then really you don't have much to worry about. You should be okay on this exam. It's going to feel a lot like any of your other, physics, math classes. It's going to feel very similar to that. That if you've put the work in on the front end doing the problems that have been assigned, you're probably going to be okay on this exam. So with that, please email me if you ever have any questions. Please work through that practice exam, and best of luck.